Oh yes, I remember this one. I use this as a teaching tool. So this is a really nice question. All right. There's a lot to unpick here in terms of like technique and what have you. First things first, we've got a volume given in centimetres cubed. I mean, it's given in standard form as well, but we've got a volume in centimetres cubed, okay? We've got a pressure in kilopascals, so there might be issues with that. We've got a temperature in Kelvin, that might need converting, or it might be okay, it depends how much we remember. And we have the gas constant R, so straight away, right, we know this is going to be a PV equals nRT question, okay? Other little things to point out, the word vacuum, right? Vacuum in flask P. Hold on a second, this is not the right tool. There we go. Vacuum in here, meaning, right, that there's nothing. So that means that all of the gas, at least to begin with, is in flask Q, which has a specified volume, temperature and pressure. So, the gas of interest is ammonia. Calculate the mass of ammonia in flask Q, okay? Give your answer to the appropriate number of significant figures. Again, we've already dealt with this once, so we're not going to have a problem dealing with it again, okay? And looking at the information in the question, they're all 3, so appropriate number would be 3. Okay, so calculate the mass of ammonia in flask Q. So we've got a little bit of work to do. To get to the mass of the gas, we're going to need the number of moles. To get the number of moles, then we need to rearrange the PV equals nRT equation, all right? So you're going to divide both sides by the RT part of the expression, and you're going to end up with N equals PV over RT, okay? All of those values are given already. So, PV over RT, pressure, 102, but we need to know our units from the ideal gas equation. It needs to be in pascals, so we multiply by 1,000. Again, if you're not sure where this comes from, you have to go and look at the lessons on the ideal gas equation and look at the kind of basics about that, but that's what it is. We're multiplying by the volume here, so again, we've got a unit issue, all right? So 1 times 10 to the 3, right? That is 1,000 centimetres cubed, right? Now, we now have to do another conversion, and we want it in metres cubed, all right? So to convert from centimetres cubed to metres cubed, again, the explanation here, not something we need for the video, but you're going to divide by 1,000,000, right? Or you could have it in standard form, I guess, okay? So that's going to be 1 times 10 to the minus 3 metres cubed. Okay? That's our top line. R is always just 8.31. T is in Kelvin anyway, so nothing needs doing there. So we bang all that into our calculator. 102,000 times 1 times 10 to the minus 3, which is 102, divide by, open brackets, 8.31 times 300. Okay. And there's our number. 0.0409. Well, actually, this is quite a long, complicated decimal, and therefore I am going to keep it in my calculator because I'm probably going to need it in a minute. Okay? So I'm keeping it in the calculator, which means I'm just writing it as this. It's actually like a weird recurring number. And I'm going to try and make sure that my answer is as accurate as possible. So again, this is kind of basic stuff, but the answer function on a standard scientific calculator is really useful for this kind of thing, because we don't know exactly what we need to do with it yet, so we're just going to leave it there, and maybe we need to manipulate it afterwards. So there's the number of moles, okay? We want to know the mass, so back to this, moles equals mass over mR. So mass equals moles times mR, okay? We've got our number of moles, mR of ammonia, 17. So the number that's in our calculator, we don't even need to use the answer function, just times 17 as it is, okay? And our answer needs to be to 3 sig figs. Now what am I doing? Sorry. Let's get back to that. 0.696 grams, okay? So, next bit. Wrong screen. There we go. Alright. When the tap is opened, ammonia passes into flask P. Okay, so what we wrote about this being a vacuum in the second part of the question is no longer true. What they're basically saying is that they open this tap and some of the gas kind of equilibrates, right? It balances out and it kind of moves into the container that was previously empty. The temperature decreases by 5 degrees C. Okay, that's interesting. We'll talk about that in a minute. The final pressure in both flasks is 75 kilopascals. So just to be clear, that's down from 102 kilopascals. That makes perfect sense because the volume has increased, right? The total volume that the gas is occupying has gone up, and pressure and volume have an inverse relationship. So the bigger a volume, the lower the pressure. So the pressure has lowered. That makes sense. Calculate the volume in centimeters cubed of flask P. Okay, so we now have to do a volume calculation. So it's still PV equals nRT. We know what N is because we had it in the previous question, right? But P has now changed and V has now changed. So to calculate V, right, we're going to do nRT over P. If you're not happy with these rearrangements, go back to basics and look at ideal gas stuff, right? I'm just assuming that you're happy with that bit, and it's the other parts of the questions that we want to look at. So V equals number of moles. Annoyingly, that's quite an awkward number, but we'll have to do it again. So from the original calculation, I'm going to generate that number of moles again because I want to make sure it's completely accurate, basically, right? So I'm doing that first sum, 8.31 times 300, to get that 0.0409 blah blah blah, because that's the number of moles that we actually want. Okay, so I'm not going to write the whole thing. That multiplied by 8.31 multiplied by, now the temperature has decreased by 5 degrees C, so it was 300 Kelvin originally. This is an interesting one. So that makes the temperature now 295 Kelvin, because whenever you change the temperature, well, it doesn't matter what unit you're doing it in, right? A rise of 5 degrees C is the same as a rise of 5 Kelvin. It's only the actual numbers themselves that change, right? What I'm trying to say is that it's quite simple, that it's not as difficult as it looks, okay? Because of the way it works. To make the temperature go from one to the other, it's just that add 273 or take 273 away. That's all it is, right? And so you don't actually have to do that, you just have to decrease by 5 Kelvin. So 295, okay? And that's divided by the new pressure, which again, we've got to be careful with, 75,000, not 75. So that complicated moles number is still in my calculator. So I'm going to multiply directly by 8.31. Then I'm going to multiply directly by 295. Not going to mess about. Okay. And then I'm going to divide by 75,000. Okay. So volume equals 1.337. And then there's a load of other numbers as well, but I'm gonna call it at 4 significant figures here initially, and then check at the very end. Times 10 to the minus 3. Now remember, this might seem like a low number. That's because it comes out in meters cubed. All right. Now here, next job is to times by 1,000,000. So that's 1337 centimeters cubed. Okay, and you might think that's the answer. It nearly is. We need to be very careful. That is the combined volume of P plus Q, because our calculation was done relative to the idea that the gas had filled both flasks, right? So it's in both of these. So this number suddenly becomes important again, because we know that actually flask Q, we were told at the very beginning it's got a volume of 1,000 centimeters cubed. So it's the difference between them. So subtract 1,000 centimeters cubed. Answer 337 centimeters cubed. That's what the total volume is. That's what the volume is just for flask P. Woo!